work CORL, Compositional Representation Learning for Few-Shot Classification by Yuille, Adam, and Alan. As stated by the title, in this work, we mainly study the problem of few-shot learning from the perspective of compositional representation learning. First, let's give a short introduction of the few-shot learning. It consists of two consecutive learning processes. The first one is meta-learning stage, where the model acquires knowledge base from the base classes, and the second is meta-testing stage, where the model recognizes novel classes. It requires the model to transfer the learned knowledge base from base classes to novel classes through limited samples. Thus, it is desired that the model can emulate human learning efficiency in transferring the knowledge. Why do we need components? The key reasons are that object components are shared among different object classes, and this kind of components representation can be learned in an unsupervised manner. Besides, the spatial activation patterns of these components are also shared, and transferring these components information might be easier than directly learning the whole object. What's more, learning components has the advantages of the robustness and interpretability. Here is the overview of our network. Our model contains four main modules. The first is the deep neural network as a backbone, and the second is the component dictionary, and the third is map dictionary, while the last one is an attention module. First, let's introduce our component dictionary. We denote a feature map as the output of a layer in neural network. We can thus obtain the feature vectors at each position on this feature map. We learn our compositional representation learnings through clustering the feature vectors. Each item in our component dictionary is one cluster center of the feature vectors in the training images. Here are some sample visualizations of the component dictionary. As can be seen, our component dictionary contains the key parts of each object. After that, we want to learn the spatial patterns as well. Given the component dictionary, we calculated spatial activation map with all the feature vectors of the current feature map, and motivated by the idea that components of different objects can have similar spatial activation patterns, and this natural redundancy can be exploited. We construct a dictionary of these spatial activation patterns through clustering, which contains the most common activation patterns in the training data as well. In the end, as not all components are equally important for representing a particular object, thus we adopt an attention module to re-weight those important components. The attention weights are computed following the SENet way, and in the end we use the skip connection to add this component-based augmented representation with the original feature map to serve as a final feature. Our model is end-to-end trainable, and our loss function contains three terms: the classification loss, the cluster loss, and the sparse loss. And during inference, we do not need to retrain any other parameters of the network. Here is the performance of our networks. The first comparison is on ImageNet variants. As can be seen, we achieve comparable performance to state-of-the-art networks. And on the CIFAR variance datasets, our model also achieves similar results. Here are some ablation studies to validate that the key design of our model. And this is the additional visualization results. And this is our conclusion as we study and demonstrate the effectiveness. Thank you.